So moving on, we now have our recovery process. So during and after exercise, our body is recovering for restoration, resynthesizing, and repairing different parts of our body. So here we have Epoch. So this is during submaximal exercise, not maximal, to start off with. So what is Epoch? So Epoch is basically the excess post-exercise oxygen consumption. So it's, in short, it's basically the extra oxygen consumed after exercise, basically to help out basically dropping back down to our resting values. So this is during submaximal exercise. So I've put here alactic and lactic acid. So here I've showed you this is where Epoch is. So if we compare this onto the graph, it will be the F and G stage. So I've literally just cut it down in short. So this orange line here, this would be our alactic stage, and then lactic acid, this will be the bottom line. I'll talk about the alactic and lactic acid part later on. So looking at this graph then, so this is basically showing the time and the amount of oxygen that we need to consume in submaximal exercise. So A basically shows the rest, and then here we see a massive increase in the amount of oxygen we need to consume. This is because exercise has started. So here at B, this part here in triangle, in short triangle, this is basically our anaerobic system. So to use our aerobic system, which is C, so this massive space here, we have to go through our anaerobic stage first. So at B, this is basically the oxygen deficit. Then at D, so here at D, this is basically our resting values along here. So this is our resting state. So like it was at A, so our resting, and then now we're in exercise. So C is basically the amount of oxygen, the amount of oxygen we've consumed in the exercise, and then E at the top here. This is basically the amount of oxygen that's required for the exercise. Right, then moving on, so here, this line here basically represents the end of the exercise, and then the rest of this from here on is basically the recovery stage. So this is what we'll be looking at more. So F, this is basically Epoch, so this is what I've got here. This is basically this picture shortened down. So F is basically Epoch, so here you have your alactic part, and then you have your lactic acid part here. G basically shows you the length of time the recovery will take. So from here, from the end of exercise to around about here, that's how long the recovery will take. That's basically how long the recovery will take back down to resting state. If it was a perfect aerobic system, we'd start off at rest again, and then we would really increase, and then along like this, and then down like this. This is basically because if we had a perfect aerobic system, we won't have to go through an anaerobic stage, so the line wouldn't look curved like this, it will look straight up like this. And also we won't have to go through a long recovery, it will literally just be straight back down to resting state. But we do have to go through recovery, and we do have to go through an anaerobic stage. So now we have the maximal exercise. So this is Epoch basically at maximal. So basically similarities. So they both still go up, and then one plateaus, however, the other does not plateau. So submaximal does plateau. Here, as you can see, it's steady state, whereas at maximal it doesn't plateau and it just stops and then drops. So if we compare both of the oxygen deficits, so here on submaximal we have a very small oxygen deficit as we're using our aerobic system. So we're not using our anaerobic system a lot. So we want to get through into our aerobic system much quicker. So we're not using our anaerobic system. If we compare to maximal exercise, we are using our anaerobic system. So there'll be a much larger oxygen deficit. So as you can see here, there is a much larger. So if we look at the VO2 required for exercise, and then the VO2 required for exercise here, there's a massive difference, because if we look at here, this is the VO2 max, whereas the VO2 max is only here on the maximal, and yet we need more VO2 for the exercise. Now if we look at the Epoch, comparing the epochs, so basically for recovery, our submaximal doesn't take as long, but our maximal does. as you can see, a much steeper gradient on submaximal than there is max. And this is basically because our muscles are working a lot harder during maximal exercise than what they are during submaximal. Now moving on to fast and slow components. So this is where we start talking more about the alactic and lactacids. So here at A, so basically A here, this is our fast replenishment. So as you can see, it's a really fast drop. D is then our slow replenishment, so this is the slow stage, dropping back down to resting levels. So A is basically the rapid decrease, and then D is the steady decrease. So the similarities and differences. So obviously you can see the massive decrease and then the steady decrease, and then later on I'll start talking about the metabolic needs and how they also affect recovery. So fast components. Right, so this is our alactic part, so this is this part. So what is VO2 used for? So basically the VO2 part in our fast components, when recovering, our VO2 is mainly used for resynthesizing ATP and PC, and basically restoring our myoglobin and hemoglobin, basically just so our oxygen can be sent around the blood and to the working muscles so they can basically restore back to resting levels. We mainly use all this through our aerobic system rather than our anaerobic system at the end of exercise. So resaturation and resynthesizing then. So for the myoglobin and hemoglobin to be fully resaturated, it has to use half a litre of oxygen, and this only takes 1 to 2 minutes. Whereas when we resynthesize our ATP and PC stores, we have to use 3 to 4 litres of oxygen, and they will be fully saturated within 3 minutes. So an example of this would be in half-time of football. So we use breaks in half-time of football basically to restore our ATP and PC, and also resaturate our myoglobin and hemoglobin so that oxygen can be sent to the working muscles a lot quicker during the exercise. So our slow components then. So our slow components mainly focus on getting rid of our waste products. So here we have the removal of CO2. So in exercise, CO2 increases a lot as our muscles are producing it. So basically, an increase of Q equals an increased removal of CO2. So the better our cardiac output, the more CO2 we'll have get rid of. So stages of removal then. So basically from the muscles use the oxygen, and then we produce heat, and we also produce other waste products. But here we're going to talk about CO2. So the muscles then produce CO2. CO2 is then transported from the carbonic acid, the carbaminohemoglobin, and the plasma. So 70% of our CO2 that we produce is transported through the carbonic acid, 23% is transported through the carbaminohemoglobin, and 3% transported through the plasma in the blood. So basically, the carbaminic acid is basically where CO2 combines with H2O. And then the carbaminohemoglobin is basically like hemoglobin, but instead of transporting oxygen, it transports CO2, and then plasma is just part in the blood. So as the CO2 is then being transported to our lungs, we then need to have very good ventilation. So our heart rate needs to be increased as well, so we can remove more CO2 during exercise. And then once CO2 is then being released after exercise, we still need a very high ventilation. We need a lot of ventilation. We need to have a very good heart rate, so we need to maintain our heart rate and cardiac output so that we can fully recover. So the removal of lactic acid then. So 65% of the lactic acid that we produce is basically transported into CO2 and H2O, which are then obviously transported out of our body. 5% is turned into glucose, 20% is turned to glycogen through the muscles and liver. The same with glucose as well. That's transferred to the muscles and livers as well. And then 10% is turned into protein. So with the glucose and glycogen, this basically is part of the Cori cycle, which I'll talk about in the next slide. But does lactic acid actually cause fatigue? That's the massive question, because some people argue that it can also be an energy source. So here I'll talk about this a lot more. So this basically proves that lactic acid can become an energy source. So here we have our aerobic system here, so the glucose, glycogen, pyruvic acid, but also lactic acid, and then we have our Krebs cycle here. So the Cori cycle then. So this basically happens in the liver and the muscles. So let's start off through this diagram then. So we start off with glucose, as our aerobic system normally does. It's then turned into glycogen, and then this is the part where we then produce lactic acid. Now, here, lactic acid is then sent to our muscles, but not only muscles, it's sent to our liver as well. So we then have lactate. Lactate is then reoxidized and turned into pyruvate. From here, pyruvate is then reacted with gluconeogenesis. So gluconeogenesis, reactive energy, basically to form glucose. This glucose is then sent back to the working muscles, so back up here, and then the process starts again. Once we have enough oxygen, pyruvic acid is then formed, and we can start the Krebs cycle. But if we don't have enough oxygen, lactic acid will then build up again, and we'll go through this cycle again and again. So is lactic acid good then? Some people say lactic acid obviously isn't good, as it can be the main form for fatigue, but it can also be a form for energy, as I've just shown, as it can be transformed into glucose and transformed into energy from there. So lactate buffering then. So basically lactate buffering weakens the effect of lactic acid. So a lot of athletes use lactate buffering, obviously just to get rid of lactic acid. So lactic acid relies on buffering capacity. So then we have our hydrogen carbonate ions. So these basically absorb the lactate and they form carbonic acid. So as we said earlier, carbonic acid is then separated to form CO2 and water. And then this are obviously not very harmful and then disposed of in the lungs. So why is it good then? This is really good because it gets rid of all the harmful stuff that lactic acid normally provides, so that we don't fatigue in our sport. So soda loafing then. So athletes use soda loafing a lot. So this is basically breaking down. This is basically providing more lactate buffering. So they use sodium bicarbonate. So they can have special sodium bicarbonate drinks and foods before events, basically to prevent the build-up of lactic acid. However, drinking these drinks and eating sodium bicarbonate and different things can cause vomiting and also diarrhea. So there's obviously some bads about it, but then the goods are obviously that there's less result of fatigue during their event. Now moving on, we have muscle glycogen restoration. So depending on what sport you're doing, it basically depends on the amount of time your muscle glycogen can restore. So during short duration, high intensity exercise, so basically in 800 meters, for example, it will take 2 hours for your muscle glycogen stores to be fully restored. So here I've got a little chart here, basically showing this will be our long duration, low intensity. So this would be like a marathon, for example. So long duration, low intensity it will take a couple of days to actually restore all of your muscle glycogen.